Hello, everybody. This is for the class Maths1141 at University of New South Wales. This is the week one work. This is just one example that we are going to look at. Remember, basically, how to solve a linear system of equation. This is just a review question for this class. So what is we have a matrix given by this, and M is unknown here. And our aim is to find out what type of solutions we will be able to get, would depend on what kind of M's, when M running through all real numbers, and what are the type of the solutions we are going to get. That's the idea. So X is equal to B is the linear system of equation. This linear system of equation and AX is equal to B, they are all equivalent. This one is equivalent to this one. It's exactly the same way in mathematics. So we write it down as a coefficient matrix and the vector X and vector B, so that we will be able to use as row operations a more algebraic way to calculate it, rather than the carrying out all the equations, which is really the burden. So that's the idea. This is why we want those ones. And also it gives us a really powerful tool, and we will be able to investigate more later on what will happen with that. Okay, this is basically the matrix multiplication. Matrix multiplication gives us this equation, or you can move from this equation to this matrix equation. So both of them the same. What is the matrix multiplication? Which does the first matrix and multiply the row of the first matrix and with the column of the second matrix. So this row will be multiplied with this one and is equal to B. This is what it means. A matrix multiplied by the vector X, so the matrix X is equal to matrix B. So you multiply this times this, you will get this. So that is M times X1. This is a dot product, by the way. This is this and this as a dot product is equal to that one. So mx1 plus x2 to x3 is equal to that number, and so on. So this multiply with this as a dot product gives us this equation is equal to m squared, and this together with this matrix dot product, this row together with this column will give us the minus m, which will give you the last equation. Okay, this equation system can be expressed as a matrix equation system like that. So then what we do, there are three different type of solutions that we are going to get. One of them is the unique solution. So this is a shortcut writing for us. So this means there exists, and this means the unique. So there exists a unique solution is one of the options that we can get. And there exists infinitely many solutions, and there exists no solution. These are my shortcuts. That exist and unique is very common in maths notations, but this is the way that I write it down things more quickly. Okay, and if there is no solution, there's no solution case? If there's no solution, the system is degenerate. The system does not make sense. I will explain later in these questions what I mean by that. You will get some kind of a contradictions. So what was the idea about getting this linear system of equations in terms of the matrices equation? We would like to first write it down instead of writing down x1, x2, x3 all the time. So we're basically eliminating that. And we are setting the augmented matrix, which is basically the coefficient matrix, which is A. And then we usually use a straight line and we put the B. So this is the augmented matrix. You know them, but I'm just repeating, reviewing. Now then we applied row operations, and to get the row echelon form or reduced row echelon form means that you have zeros underneath. You have 1, 1, 1 on the some kind of a diagonal. You might have 0 here, you might have 1 here. It may sort of shift depending on the situation, but you is somehow you have a 1, 1, 1 and zeros in the down and the something on the above. That's a structure for the reduced echelon form. Reduced echelon, I mean, the row echelon form for the reduced one, which is a complete reduction, which means that you have an identity matrix in a corner, which means that this needs to be 0. Because if you have this position, you can multiply this row, whatever it's there, and you can subtract it, right? You can get rid of this one and make it 0 if you have this structure. So why not? You reduce the more and get the fully reduced form. With that way, in the end of the calculations, you will be able to see directly what is the result, what is the solution. This is why I like the reduced row echelon form rather than row echelon form. It is possible to use the row echelon form, but you need to go back to the equation form in a bit earlier than the fully reduced form. Okay, we would like to find the unknowns. The unknown vector is here, as we know, is x1, x2, x3. This is the unknowns. This is the, and m is a fixed number. We don't know yet. Our aim is to figure out what kind of m's gives us what kind of solutions. That's the question that we are dealing with here. So, if we change the R1 and R2 because we wanted the leading coefficient 1, so there's a 1 here, so take this one onto here. That makes that change the row 1 and row 2 is a sensible thing to do. That's what I've done here. So we have 1 in the corner. We are happy with this position, but we are not happy with those ones. We would like to make this one 0 and this one 0. So if I multiply with the row 1 with m minus m and add to the row 2, which is this row operation, and if I multiply the row 1 with minus 2 and add to the row 3, then I will get this position 0. And then you calculate, right, whatever those numbers are correspondingly. So this one, by multiplying m, you have 1 minus m squared. Multiply this by minus m, you will have 1 minus m, which is this position. Minus m squared, we have done nothing in the first row. First row was exactly the same. And then the second, this row will be the minus m times this, adding here. So that will be gone. Minus m squared plus m squared will be gone. And for the last one, so this will be 0. This will be 1 minus 2m because we are multiplying minus 2 to the row 1 and adding to the row 3. Then if you multiply this by minus 2, you will have 4m minus 2. So you have 1 minus 2m here. Here, if you take the 2 out, minus 2 out, you have 1 minus 2m. So you have 1 minus 2m, 1 is 2m. And you can simplify this one. You all here you will have minus m, 1 minus 2m as well. So 1 minus 2m, it will be common factor in this last row. And here we can organize it or a little bit simplify this as a multiplication, taking a minus 5 out. We have m squared plus m minus 2. So this can be factored as a linear factor, m plus 2, m minus 1. So that's this position. So this number will come here. So in order to be able to divide this with a common factor, we have cases. Because we don't know m. M is just a fixed real number. We don't know what it is yet. So we are assuming that is a fixed, but it runs through the all real numbers. What will happen if 1 minus 2m is equal to 0? Then you will have this 0, this 0, this 0. So all of them will be 0, right? We need to think about this possibility. If this is equal to 0, m is equal to 1 over 2, and then by putting the m is equal to 1 over 2 into this matrix, you will be able to get this matrix, right? And then the last row, there is no contradiction because everything is 0, right? The last row basically says 0x1, 0x2, 0x3 is equal to 0. No contradiction. So there is no degenerate case. There are some solutions. It will not be unique, but it will not be, there will be some solutions because this is consistent system. This last row makes sense because 0 is equal to 0, right? It makes sense. So this is not the reduced row echelon form yet. So we would like to get the reduced row echelon form in order to be able to find the solution. So simplify, divide this one by 4/3. Then you will get 1 in this position. Then you can get this position 0. And applying this row operation, you will find this reduced row echelon form. As you see, there exists an identity matrix in a corner, and whatever they are. So this is a leading coefficient. Since we have 3 unknowns, but we found only the 2 leading coefficients. This has 1 leading coefficient, there's another leading coefficient. We have 2 leading coefficients. That means that we have to have infinitely many solutions because one of them is a free variable. So from the third row, or from the third column, actually, we will be able to say that there exists a free variable. So x3 is a free variable. Sorry. That is, let's say lambda 3 is equal to lambda, x3 is equal to lambda. Then from the first row, we have x1. So we are going back to the matrix multiplication case. So we have this row, we are multiplying with the column row x1, x2, x3. This time x1, x2, x3 gives us x1 plus x2, 0, 0, x2 plus 2/3 x3 is equal to minus 3/12. So that's the first row. From the second row, 0, x1, 1, x2, 2/3 x3, which is this guy, which is equal to that one. Lambda 3 is equal, x3 is equal to lambda, is a free variable. So this is a free variable that we choose. Taking the other side, take this one on the other side, we have x1, x2, x3 as a vector. So lambda could be any real number. It's running through all real numbers. Then we can rewrite the solution space. Let's say S is a solution space. This is the set of the vectors of this kind. So minus 53/2, 25/3, 0. This is the coefficient. This is the constant term in this vector, right? This is the x1, x2, x3 vector. And that's the constant terms, constant coefficients, constant terms of the vector. And the lambda minus the coefficient of lambda, this is x1, and x1 equation, the coefficient is minus 2/3, which is this one. In the equation x2, the coefficient of lambda is minus 2/3, which is this one. And the coefficient of lambda in the x3 is 1. And there's no constant in x3, so this is why you have 0 here. And lambda is running through all real numbers. So this is a solution space. What is this solution space? This is a line in the real three-dimensional space, right? Because it is one-dimensional, and we have 3 components, x, y, z, or x1, x2, x3. So these are vectors in R3. So we have vector, and we have, this is a point that the line passes through. And this is the vector that the direction vector of the line in R3. So this gives you a line in R3. It means that we have an infinitely many solutions because lambda runs through from minus infinity to plus infinity. We have infinitely real numbers for each lambda, for all lambda. Then we have infinitely many solutions for this case. What was the case again? When we assume that 1 minus 2m is equal to 0, we found an infinitely many solutions. Okay, so we need to think now, assume that 1 minus 2m is not equal to 0. If that is the case, then we can divide the last row with 1 minus 2m. As we see here, that was the common factor, right? Here is 1 minus 2m is the common factor. If 1 minus 2m is not equal to 0, we can divide it to everything. If we divide, we have 1 here, minus 2 here, and minus m here. This is what I have here, right? That's the case. Again, now we need to solve this equation. Well, this one here is 1 minus m, 1 plus m. We have this one as a common factor, and 1 minus m will be a common factor here and a common factor here. Then we can divide it, but you cannot divide directly. We need to assume whether it is 0 or not equal to 0. There are two cases that we need to search. We need to look at it. So if 1 minus m is equal to 0, which is the case when m is equal to 1, then we will put m is equal to 1 in here. Then the last row again will be 0, 0, 0. And that will be 1, and that will be minus 1 square 1, which is minus 1, which is minus 1. And that is 0, this is 0, this is 0. So we should have, again, an infinitely many solutions. But it is not reduced yet. So in order to be able to completely reduce, fully reduced, we want to disposition 0. So this is why we have R1 is equal to R1 minus R2, row operation applied to it. So as we see, there's an identity element here. We have leading coefficient for x1 and x2. And x3, there is no leading coefficient. So x3 has to be the free variable. And also the last row says that x3 is free, right? So from the first row, we have x1 plus 3x3 is equal to 0. From the second row, we have x2 minus 2x3 is equal to minus 1. And let's say x3 is equal to lambda, and then x1 will be minus 3 lambda, x2 will be minus 1 plus 2 lambda. So x1, x2, x3 is the unknown vectors. And the solution space, as we've looked at before, will be the coefficients, the constant terms in this equation, which is 0. Yeah, I think just a minute for me. So this is 0 minus 1. That's what I find 0 minus 1. There is no constant term in this part. There's a constant term here, which is why we have minus 1 here. And the coefficient of lambda will be minus 3, 2, and 1, which is that guy. Again, lambda is any real number running through. So this is one-dimensional objects in three-dimensional space. It is a line. One-dimensional object in three-dimensional space is a line. So it is a line. Solution space is a line. So that in that case, we have that exist infinitely many solutions. I can put that exist here too. Okay, now if 1 minus m is not equal to 0, what is the situation? Then we can divide the row that we obtain with the 1 minus m, right? So that was, where was the situation? This one here. This was the case, and we looked at if what will happen 1 minus m is equal to 0, and what will happen if 1 minus m is not equal to 0. If it is not equal to 0, we can divide 1 minus m to this row. You can apply that row operation. If we do that, we will have all this will be gone. We will have 1 plus m here, 1 here, 5, m plus 2 here. So this is what it is here. Yeah. So this is the situation when 1 minus m is not equal to 0. Dividing that, we obtain this. Okay, this one, we want this position 0. These are the leading coefficient. Leading coefficient is perfectly fine. And these are 0, perfectly fine. Now, next thing to do is we would like to get this position 0. In order to be able to do that, we multiply this row with 1 plus m and add to the third row. That will make this position 0. And then figure out what are they coming. So if we do that, the minus 2, 1 plus m will plus m will give us 2m plus 3, which is this one. If we multiply minus m with 1 plus m, adding to 5m plus 2, we will simplify a little, and then we will get m squared plus 6m plus 10, which is this one. Now, the situation depending on 2m plus 3. If 2m plus 3 is equal to 0, then m is equal to minus 3 over 2. Then this number will be a number if you calculate it as I've done here. But this is not 0. This is minus, this is 13. It's a number. 13 over 4 is a number. It's a real number. It's not equal to 0. But you would have 0 here, and then this row will read like 0x1, 0x2 plus 0x3 is equal to 13 over 4. This is a contradiction. This doesn't make sense. So this is this is a degenerate case. So there exists no solution. 0 is equal to a number, which is impossible, right? This is what it says. This last row reads as 0. So this part is 0. 0 is equal to 13 over 4. It is impossible. It's a contradiction. It doesn't make sense. It is a degenerate case, so there's no solution. Okay, so another situation, another possibility is that 2m plus 3 is not equal to 0. If this is the case, we can divide this row with 2m plus 3, make this one is 1, because we want leading coefficients, right? Thus, in this case, if we do that, we will obtain 1 here, and we have a rational polynomial here, and we have this case. It has to be a unique solution because we have 1, 2, 3 leading coefficients. It doesn't matter those numbers. For every m, you will be able to find if m is not equal to 2m plus 3 is not equal to 2m minus 1 is not equal to 1. All this situation, m is anything apart from that exists a unique solution. I've done it here as a here. There exists a unique solution if this unique solution is always the case if 1 minus 2m is not equal to 0, if 1 minus m is not equal to 0, 2m minus 2 is not equal to 0, then you always find a unique solution. If this is not equal to 0, this is not equal to 0, but this is equal to 0, no solution. It is not equal to 0, but this is equal to 0, we have infinitely many. And 1 minus 2m is equal to 0, we have infinitely many. So this is the summary of our all calculations that we've done for this question. Yep. And this is a really nice introduction, really nice recall of the subject. This is another way of writing it. M is equal to something. M is equal to 1 over 2 or M is equal to 1. We have infinitely many. M is equal to minus 3 over 2, no solution. M is not equal to 1 over 2, not 1, and not minus 3. We have a unique solution. It's a summary. This is a conclusion. So in the question that you have in your hand, we have the maple codes. I've done it from the scratch in order to be able to explain step by step and remind you how to solve the linear system of equations, like a review. But if you look at your questions, it tells you exactly what you need to check for. In the codes, it is given to you M4 in this way. It means that as row 3 needs to be multiplied by that. In order to be able to do that, you need to assume this is not equal to 0, right? Then in a corner, you need to check if it is equal to 0, what will happen. And then you put m1 over 2 into this equation that is given in the paper for you. And then you will solve the system. So instead of doing the very long calculation as I've done, your calculations will be very simple in that way. And yeah. And similarly, you will look at the row M5 and you will see that row 2 is divided by 1 minus m. And that means that you need to assume 1 minus m is not equal to 0. And you need to check what if m is equal to 1, what will happen, what is the solution of the system that you need to solve. So m is equal to 1, put m is equal to 1 in the matrix that is given to you. Because the row operations results are given to you. That will be much more easier than the calculations that I've done one by one. And then the last part of it, you will assume m is not equal to 1 over 2, not equal to 1. Then you will end up with this matrix, which will be exactly the last part of the solutions that I've done. And you need to do that. You need to do this part. But by just reading the codes, the calculations will be a lot less. You don't need the row operations to see. I've done the row operations to explain it. I think that's all for this question, and thank you very much. All the best. Thank you for listening.